So in this lecture, we continue talking about a continuous ergodic theory. And so we continue to assume where our ambient space is compact metric. And remember, M of x is all Borel probability measures on the space. And the weak star topology on the measures is given simply in terms of the convergence it implies, that measures converge if and only if the integrals against all observable functions, continuous observable functions here, converge. And this is a metrizable topology, so I won't write down the metric again. We may need it in some applications. But this is a nice metrizable space, and it's even compact. When X is compact metric, then the collection of Borel probability measures with the weak star topology is also compact. All right, so it's also convex, which means, I'll define this in a little bit, but this convex combination, the line between any pair of points, is also in the space. So that's pretty easy. This is a it's clear this is a probability measure because the sum of the, you get a measure here, and they add up to 1. And it's a measure of countable additive and all that stuff. So our dynamics are induced by a continuous onto map. So I wrote affine here. That's part of F star, not F. So I'll have to fix that. So it induces a map on the, let me censor this here. It induces a map on measures by push forward, as it's called. So F star of mu, the measure of B, is the measure of F inverse of B. So you take B and you want to know its measure. You pull it back to its inverse and compute the measure there. And that gives a measure over here. And this F star, when this is continuous, it induces a continuous map on these guys. So we start with continuous map on a compact metric, and notice what happens when we pass to this larger space of objects. We still get a continuous map on a compact metric space. All right, now in terms of the dynamics, what we're interested in is invariant measures. So the space of invariant measures is called MXF. So that corresponds to fixed points, if you like, of the push forward operator or the induced operator. Sorry, the induced map. It's not an operator. Well, let's just call it the induced map. Don't want to get it confused with the Koopman operator. And so we also get the fact that, well, this guy is compact, and this is also compact. And of course, it's metric because we can restrict the metrics here. All right, so how do we see it's compact? Well, it's enough that it's closed because the ambient space is compact. And so let's do sequential check closure by sequences. So if we have a convergent sequence, F star is continuous, and so F star of this, but each one of these is UN. So the UNs converge to F star of mu, UN converge. We're in a metric space, and so that must mean that F star of mu is in mu. And F star is affine, and if we have an invariant, a pair of invariant measures, then this is an easy calculation I won't go through. Because it's affine, then you get the affine combination, or the convex combination is contained in the invariant measures. All right, now what we don't know at this point, so you have to be careful when you do mathematics, is not to spend too much time proving stuff about a set that could be empty. So there's a famous theorem, important theorem, due to these guys, that says in the context of compact metric spaces, continuous functions, there's always at least one invariant Borel probability measure. All right, now remember that the Borel probability measures that are invariant correspond to fixed points of F star. So F star is a continuous affine map of this guy, which is a compact convex set in the weak star topology, and there's fixed points theorems, infinite dimensional versions of the Brouwer fixed point theorem that will yield it just for free, but I'm going to give a direct proof which also shows a little more clearly where the invariant measures come from. All right, so here's the theorem. Let's say we have a continuous function on the compact metric space, and we just start with any probability measure. All right, and then we push it forward, we iterate it and average it. So we push it forward, iterate it, and average it. All right, so we take the measure here, whatever it is. This isn't a very good picture, but we'll see. And we push it forward, but when we push it forward, after 2 steps, we average these two. After 3 steps, we average. All right, so that keeps it a probability measure, right? Because here we add these guys up. We're going to get mass 1, total mass 2, total mass 3, but we divide by 3. All right, and then, of course, this is probably not an invariant measure, but we pass to a limit in mx. All right, so remember, well, such a limit point exists because mx is compact, and therefore we have a limit point, and the limit point is an invariant measure. All right, so I've already said this, but let me say it for the record here. Because, remember, this guy is compacts, the space of Borel probability measures, it's convex. All right, well, first I have to make the point that UN is contained in that. So I kind of said that already. But this linear combination of measures is a probability measure, a Borel probability measure. And also MX is compact with the weak star topology. So there's some limit point. All right, so a basic property of compact sets that infinite subsets always have a limit point. So here's some preliminary, so I can just give the proof as a single line of inequalities. If we have the integral of alpha composed with, so this is just, well, this is just a general fact about integrals, but I wrote down the formulas that we're actually going to use, the specific case. But we've seen this before, is when we do this integral, we do a triangle inequality, and then you can bring the soup of this guy outside. Notice this is a nice continuous function in a compact space, so in fact it has a max. This integral is 1. All right, so an integral that looks like this is always less than or equal to the 0 norm. The second thing is change of variables. We have, if we integrate df star to the I of gamma, remember we can, well, we did it with 1, but it also worked with iterates. You saw this in a homework problem. We can bring it in and we get this. And the last fact is just a theorem from last time that a measure, a probability measure is invariant if and only if when you integrate against all observables, alpha composed with f versus alpha, and you get the same answer. So in terms of, it doesn't say that alpha is an invariant set, but on average, alpha composed with f has the same average as alpha. Okay, so that's, well, of course, this way, remember, was easy because f star of mu equals mu, and that's the same argument as here. All right, so here's the line of equalities, inequalities I promised. So we pick some alpha, so we have to show it's true for every alpha, and so we just pick one and show it's true for that, and that'll suffice. And we take this difference, and we want to show that this difference, in fact, is 0. Okay, so what do we know? Well, the starting point is that we're assuming that u is a limit point. All right, so we're assuming that mu is the limit point here, and it's in the weak star topology, so that means the integral against every observable converges. There's a d mu here missing. Then we can rewrite this integral, since we know mu is a limit, we can rewrite it as this limit. So because of this convergence in the weak star topology, and then in this stage I take the definition of this and plug it in. So now it's a little messy, but we get d of this and then d of this. I should probably put square brackets here. All right, and then we're going to use the change of variables here. So here's, remember, 2 was the change of variables. We're integrating alpha d f star. We bring that inside, and we also distribute the integrals. And we still have the 1 over nj outside. That's part of the definition of this. I brought the 1 over nj out for both the terms. And then we get this term. Now, this happily is a telescoping sum. This is just one index more than this. So we end up with just the 0th term here and the njth term here. The I plus 1 gives an nj here. All right, and now we're going to integrate this. But now we do standard trick. 1 over nj comes outside the absolute value. And this integral we write as, well, plus the opposite of it, take the absolute value, and then do a triangle inequality. But now we use fact 1, that this guy is less than or equal to the norm of alpha 0. That was fact 1 here. That was the first thing we did here. And that this is also less than alpha, the 0th norm of alpha. And then we still have a limit out here, and this limit is 0. All right, so that's the proof in one long line. You can mainly just follow your nose to get convergence or equality here via this convergence. All right, now often when this is illustrated and in fact put to use is you start with point masses or delta functions. So I haven't defined these before. So at a point x, define the measure of b to be 1 if x is contained in b, and 0 if x is not contained in b. All right, so in particular, delta x of x itself is 1. All right, so this you think of as an infinite spike if you know about delta functions, which are, properly speaking, measures or distributions. So you think of it as an infinite spike above 1. All right, or which gives total mass 1 to the point x. All right, now f star of delta x corresponds to the delta function at f of x. All right, so that should be easy to check. So when we want to push forward this measure, what we get is the indicator function of, the delta function at this point. Okay, so it also happens to be the indicator function of the point, I guess. So now let's rewrite mu n that we use to construct the measure by taking limits here. And when we do that, we see that mu n using this fact is 1 over n, the sum of the delta functions. All right, so this says go out n steps, or n minus 1 steps, and then average the point masses on these guys. All right, and so this guy wanders around the space on the iteration, but on average, you take some kind of you take exactly a weak star asymptotic average of these measures on longer and longer orbit segments. So here's kind of a simple example. It's a little, it illustrates one type of convergence. Is let's look at the north-south pole on the sphere, for example, pick a point x, and we average the delta functions along this. All right, we get mass here, mass here, mass here, but there's a 1 over n. So the mass ends up converging to the invariant measure of the fixed point of the south pole. All right, now another example, which I didn't include here, is you take rigid rotation on the circle, and then say with an irrational rotation number, with irrational rigid rotation, not very good picture there. And when you do that, you get orbits that are dense in the circle, and when you average the delta functions along that orbit, in forward time, in the weak star topology, you end up with Lebesgue measure on the circle. All right, so this is sometimes referred to the fact that the orbit is equidistributed in the circle because the averages of the delta functions along the orbit converges to the ambient Lebesgue measure. All right, so as with a lot of things in ergodic theory, we need a little more equipment to understand the next step. And here's some definitions which you may have seen, perhaps not. And this is a general measure theory definition, but we're going to use it on Borel measures in a compact metric space. But here is one important definition. So mu is called absolutely, so we have two measures, all right? So we have two probability measures here. And mu is absolutely continuous with respect to nu if nu equals 0, if for whenever B has 0 measure under nu, then it has 0 measure under mu. And this is also often written as mu less than nu, or red. Mu is absolutely continuous with respect to nu. So here's the standard example. Let's pick an L1 function that's positive and has total mass 1 and define a measure. We're given nu here. We define a new measure, mu of B, to be the integral of phi d nu. All right, so clearly then, if nu of B is 0, then you're integrating over a B 0 measure set, and therefore mu of B is 0. All right, so this is the standard example. And the Riesz representation theorem says that this is, in fact, the only way it happens, and that this characterizes absolute continuity. So let me state, I said Riesz, I should be saying Radon-Nikodym theorem. All right, so let's start with two probability measures, and mu is absolutely continuous with respect to nu. Then there exists a phi like we just had, a phi that's L1 bigger than or equal 0, total mass 1, and the mu measure is given by integration against phi d nu. And this works for all measurable sets. So phi, there's a notation here. Phi is often written as d mu, d nu, and therefore heuristically, as you have with calculus, d mu equals d mu over d nu, and then you integrate both sides of this to get the formula for the new measure. All right, so the integral over b, so this side is then mu. All right, so this side then is mu of b. All right, so there's language for this, as there is for most mathematics. So there's various names for this, but the most common is to call this the density. So this phi, sometimes it's called the derivative, of course, and you'll recognize this formula as the U substitution in calculus, if you like. And that's called the density for physical reasons. And notice there's no uniqueness here, but you're in L1. All right, so functions which agree almost everywhere are in the same L1 class. And of course, they give the same integrals. So it's unique it's a unique L1 function class. So remember, we have this traditional sloppiness of writing elements of L1, even though we know they're equivalence classes, we write them as a single function. And in physics or elementary calculus, you learn the floor, you think of this as you're on a wire with variable mass, a variable density, and you want to figure out the total mass of the wire from 0 to x. And then you know the density, and so you integrate. The density tells you mass per unit length, and then you have the heuristic formula, or the formula in terms of infinitesimals, dm equals rho ds. So rho here is the density along the wire, and then the total mass you get by integrating. All right, so we also need to know something about convexity. I've already kind of used this language, but I'll make it more formal now, or more explicit. So we're living in a vector space, so it also works in a more general affine space, but we'll always have vector spaces. A convex combination is what we said before. It's this particular linear combination, but where these guys add up to 1. All right, it's called non-trivial if p and 1 minus p are both non-zero. And then you say z is between x and y, where x is different than y, if it's a non-trivial convex combination. So that's the same as saying it lives in the interior of the interval between x and y. All right, so a set K, again, in a vector space, is convex whenever you have a pair of points in it. All the convex combinations made by the 2 points are in K. All right, so another way of saying that is every point between x and y is in K. And the other definition is that an extreme point of a convex set is a point z that's not between any x and y. All right, so this guy is not extreme. Here's an extreme point. Here's an extreme point. So you have a supporting plane here. I won't draw it, but there's a tangent line or a whole family of supporting lines. So that's more convex stuff, but we don't need the supporting hyperplanes at this point. Okay, so we know that mx of f, the space of invariant measures, is compact and convex. And now we want to study this convex set a little more. In particular, what are its extreme points? So extreme points are exactly the ergodic measures. That's what the theorem says. So intuitively, what it means to be an extreme point is you're not a combination. You're indecomposable, right? Where you think of a convex combination as a decomposition. All right, so it shouldn't be surprising that the extreme points of the space of invariant measures are exactly the ergodic measures, remembering that this guy is convex. So I'll do half the proof now and half the proof next time. So I'm going to prove it's an extreme point, then it's ergodic. All right, so we're going to go contrapositive, so assume it's not ergodic. And by the definition, that means there's a measurable set which is invariant and has measure strictly between 0 and 1. All right, and now we use it to define a pair of measures. All right, one measure, the stuff that's inside E, so given B, right? So given a set B, for a Borel set B here, define mu1 of B is to the relative measure that's inside. Now notice we're normalizing by the measure of E, which is not 0 here. And then we have a second measure, which is the relative mass of B outside of E. Again, normalized here. When you say relative, we say proportion. All right, so it's easy to check a bunch of properties. First, that these guys are probability measures. That's what the normalization buys for you. Second is that since E is an invariant set here, all right, E is an invariant set, these measures are invariant measures, all right? And in fact, so they're invariant measures and they're not equal, all right? And so we get that, again, just using the definition here, so let me not get ahead of myself, that since B can be written as the disjoint union of the stuff E and outside E, then we can write this mu as a linear combination of the measure of E, that cancels this denominator, and the measure of E complement. But the measure of E complement is 1 minus the measure of E. All right, we're in a probability measure. And this thing that corresponds to P is strictly between 0 and 1. So we've written mu as a non-trivial convex combination. So that implies that mu is not an extreme point. So we'll do the other way next time.